Welcome to Renaissance Charge Videos. I'm Rick Friedrich again, and I am going to talk to you, continue on from the last motor video after we just did the Don Smith series. I've been waiting to do this video until I uploaded all those together in one shot. So in this video I'm going to continue on with the upgrades that we have on this motor in regards to the dual Hall as we showed with the bigger motor. So we've done the same thing with this, and this is what we'll actually include in all the kits that are ordered from this point. Some of the orders that still haven't gone out. I've been kind of waiting on to do this upgrade. So thank you for your patience and waiting, and it will be worth it for these benefits. So again, what we have is a couple of things. One is that we're using the Arduino with the UNO with the chip here, the removable chip, and this way any upgrades that you want, we'll just charge you for the chip. We're not going to make any money off of it. That way you don't have to send the whole board in or replace the board with any kind of change. So what we've done now is we've added the double Hall and self-starting. So the way you need to do the self-starting is with two Halls, because you have to advance or retard the timing quite a bit for it to start itself up, as we're going to see in a moment. As actually we saw with the last video with the larger 4-pole. That way we don't have to give this thing a big push. Now, this does require the double spacers in here in order to do this. In order to do it with the single spacing, we'd have to really, I don't know if we can even do it. It would draw quite a bit of amps, which we'll see when we run this, just how much, and we have a limitation on the amp draw from what it could be. But even with that, it still draws quite a bit at startup. So those are the two different things. The Arduino, the bottom part of the board, so it will fit into all of the previous green boards here. And the only other change from when we started was essentially, well, there's a couple of changes, but the main one is adding the capacitor. So this video is going to be about the capacitor again, and we're going to go to 24 volts. This is a model for one of my customers, one of the orders that has to go out. So I told him, I said, okay, well, I'm going to be doing a video, and this is the model that he wanted. He wanted the double spacers. So in other words, it's not that much of a drag on here. And then the other upgrade, I'm going to mention it here. I do have new rotors. So we made one change. So this is the third model of these bigger rotors now. So now we have a straight hole right through, 1/4-20 all the way through. There's no balancing issues. This is still the one with at 90-degree angles where we have to put the plugs in. This one is pretty balanced even without the plugs. You'll see very minimal vibration on it, but this one has really no vibration now. So any new orders from this point will have those rotors, so they don't need the aluminum lugs in there. So those are the latest upgrades, and there isn't really much after that, so it's not like we're going to be constantly changing all this. Where we will be getting into changes is with the output, as I mentioned. the output of the generator coil, which is going here to this variac and this light here, and the output going to the charging battery will have eventually accessories so you can do the resonance process on the output. And that's where the Arduino is important for us to tune the motor with the Arduino to the particular output that we're using. So that's coming later this summer, hopefully. And that's complementary to the Don Smith systems that we're focusing on right now on the YouTube channel and in the book, the upcoming book. So all this stuff overlaps, both in the solid state and in the motor setups. There will be doing the same kind of thing. So we have 24 volts powering the motor, 24 volts charging, and then we have an output right here. There's still quite a bit of torque left, but not as much with the double spacing. So let's look at that right now. So the only other thing to mention is with the particular code that I provide, in order to turn it up, the code should be made for 12, 24, 36 or 48 volts separate code. And there's just one little adjustment in the code that we make, in which essentially this potentiometer or variable resistor here, when we turn it up to full, when we turn it to the right, it's full power, and as we turn it down, it cuts off the on time, the percentage of on time. Well, the thing about it is, as this speeds up, we have to cut back more and more on that on time because of the RPM. So after a while, or after it gets up to a certain speed, then it overlaps itself. So we have to cut back. And you'll see here now that I'm on 24 volts. If I go right up to full, you'll see it sort of bog down a little bit. So that means if we wanted to adjust the code so it didn't do that, we would have to make a slight adjustment, just one digit lower. So that means when we go up to 36 volts, it's going to do that sooner. So we can't turn it all the way up to full. So you can still use this system at 36, 48 volts, but you just have to turn that down. Otherwise, it will overlap itself. That could be really bad. So, and you'll see if you slowly turn it, when the RPM just starts going slower rather than higher at that point. So that's why I was wanting to do this and provide with the kit different chips that have different voltages, different voltage ratings on them. And then if you want to go from one to the other, you just change the chip out. Everything else is the same. So that's kind of what we're moving into. By the time this video is uploaded, we'll be doing that with orders. Well, it'll be two chips, 1224, 3648 volt. So here is a double stacked. So normally people get the single stack, but this is a double. And so there's twice as many MOSFETs and related parts on here. And the other thing to mention is, again, the capacitors that we have across the MOSFETs, and that is the drain to the source, not the gate. We're not talking about putting a capacitance across the gate here. So I've got 2.2 microfarad capacitors across each MOSFET. We've got one MOSFET for each of the four coils on the top or the bottom layer. And then they go to a very fast diode. Now this particular customer only wanted to run the generator output. They were not going to put a load on this, so that we're going to limit the diode on here to the one that we normally provide, and just one. Whereas if you were going to load this down with the single spaces, you'd have probably a higher amperage diode, or put a heat sink on this diode because it will be stressed. It's a bottlenecking point right there. And in relation to that, again, I've said before, if you're really going to do this seriously, you're not going to use clips. You're going to use solid connections, big wire. So I've already talked about that in quite a bit of detail in the past, so I won't need to go into that anymore. So let's run this, and then I'll bring the camera closer so that you can see it this time and walk you through, for those people who want to know some of the assembly details. They can see it here now, and I'll walk through that. So let's watch the details here. Let's see if I can get this ammeter in a place where you can see it. Just tell me if you can see it or not. I like saying that, it's funny. That may hold, may not. Now the amperage here is going to be different after the T. Oops. Like on the positive side, you're going to see so many amps here. And then there's more from the charging battery. So the charging battery actually provides amperage to run the motor itself, and then it charges up too. So I'll show you that in a minute. So anyway, we are setting our pot, and then we're just going to start running it, and we can look at the oscilloscope. So watch either the amperage or the oscilloscope. You'll see quite a bit of impulse into this, or you can watch the motor start up. So it's going to take a second, and then it's going to bounce around a little bit. See, it corrected itself there. Depending on where you place the hall, you can see it's coming down now. It's going to go all the way down to like 3 amps only, which is fairly low. I didn't even put the bearing grease in there. I forgot to do that yet. So you can see the spike. It's come down. It was over 100 volts to start, and then it came back down. So really, to go over that voltage, you really want a bigger FET in there. That's a higher voltage FET. So then we can turn this on. The load. You can still see the motor is running with that really fast RPM there. It's over 5,000 RPM. Then I can go up, which is really bright now. It's going to get hot. So we're only at, now we're drawing more amps. So come back down, speeds up. Already covered these details. We're charging the charging battery. the input, 24.6, not really draining the battery that much. So you can see 4 amps right here. If we go over here, it's 6 amps. So that's including, that includes the charging battery. So what's actually going in here after this T, where the input positive and the charging negative wire, which these are really the same connection, you can see I've already connected it there anyway. That means we've got 2 more amps that you have to count for. So anyway, this doesn't even need this pad anymore. There's not really any vibration in this. But I did put the little bearing. So now when we disconnect it, make a solid disconnect. Don't reattach it while it's spinning. So everything's pretty cold here. It's all running well. And I could have turned it up and down a little bit more. But we've already covered these things. So let me bring around the camera. We can look at this for those who want to know details. All right, so the battery charged a little bit. Of course, 6 amps. It's not going to push it too much, but so here we have, first of all, the LED, just with the bridge and that yellow cap that we use, and this is just in reverse with the variac there. So I have the generator coils all in series with each other, and they're pretty high voltage. At 12 volts, it was 56 volt output, and it's 19 gauge wire. So there's 4, these are the generator coils here, every other one. And this is the motor coil on the corners. And so what we do is run them in series, and then I brought the wire back down. So this is the one output wire, there's the other one, and then there's a crossover right here, this wire. So up, down on that, and then the motor coil wires are all in parallel. So we have 4 red wires on the top coming together, equal length. That's why it's kind of looped around here so that everything's equal. It's not ideal to loop it like that, but people value neatness over efficiency. That's why sometimes you see a lot of mess with my wires, because I'm actually making it more efficient. So anyway, then 4 black wires on the bottom come together, and so then there's 2 separate input-output wires to the motor going down to each FET. So let's move over there and take a look at the details. First of all, this is the new rotor. Like I said, it's 1/4 all the way through, so we don't have an imbalance issue at all anymore. That's not what's on this rotor, as I said. I've had to put these plugs in there to balance it out. It was just something that I did without thinking when we made these rotors. So, but they work fine with the plugs in them. So anyway, these are the two hulls. The hull is facing downward, so the face of it is facing towards the south pole, which is facing up in this case. So the bottom rotor, one of the magnets will have an S on it to indicate south, which I think is right there. Yeah, you can vaguely see it. Barely see the S. And then the other ones, the magnets will be facing down, and they'll say N on them. So obviously the top will be the south pole. So again, the hull triggers by the south pole. Now you could switch it from the north side on the reverse, and it will work, but it's problematic trying to switch the hull off of the motor coil or the generator coil, because when it's being pulsed, it will give a different signal, and this is really critical with our code in relation to the hull. So we really want it over here. We could stick it on the bottom, but then again it could get knocked around down there. So so this is really the best place to put it. And what we've used here is just a 12 gauge magnet wire here as a support, and then we just clamp it with this loom here. Just put a knot over top of it. So then we wire tie it right here and make it secure and all that. But so that's essentially it. Like I said, the coils, the lettering faces down. So on the bottom of the rotor, or on the bottom of the coils, the lettering is there, and you can see the double spaces there, as opposed to the single space. So that's the difference. Now I do put some hot melt glue to make sure that these coils don't turn around or rattle around in there at all. But what I've done also is put holes in you can see in the frame there on the inside, so that the air can flow through there, and like a Tesla turbine, it sucks the air in so it can cool off these coils. If you push them above an amp or so, they start getting warmer. And then if you're pushing them to 2 amps, even though they're rated at 3 something, they still can get hot, and you don't want to have the thing have thermal run away and melt down. So it's a pretty simple system. We put lock washers and flat washers between each layer here, and we compress it. And for those who are assembling this, make sure you realize that the magnet flange is on the outside of where the coils are, so you can see the flange sticking out there on the bearing. And on this side, it's the opposite side on the bottom there. So that way the spacers go, so the flange of the spacer is touching the rotor, and the smaller side is in the inner side of the bearing race. So that's really all. Oh, the other thing is, like I mentioned, is if you look at, oops, too close, you can see kind of a flat right there that I've filed out. So from this point on, you'll have all the flats will be 180 degrees and you need to, well, you don't need to make that much of a flat, but if you want to pull the rotors off, you want to flatten it enough so that like it actually scores the shaft quite a bit so that it's difficult to pull it off if you don't put a flat on it. So that's pretty much it. Oh, the generator coils, like I said before, they're in series with each other, so when you're assembling it, you can see the one wire there, how it's going from this coil across over to the other coil, and then again goes down to this one. It crosses over. And then the motor coils, oh yeah, the motor coils are not on the corners, sorry, the generator coils are on the corners and the motor coils are on the sides. And see, it doesn't really matter where we place the Hall as long as it's above the magnet. So again, if you look at the angle here, you'll see where this is pretty much at top dead center, especially at the high RPM, we want that. But at the beginning, it wants to be over here. So that's why we have a separate one. So you can see these two sets of wires here. So it's the white wire then. So for those who want to upgrade in this way, the difference is on the board. We already have these 4 pins here. So the 2 center ones activate, so pin number 4 and 5 right there in the center. If you put the jumper across there, which we provide with the kit, that will activate the battery swapping. So pins 3 and 6 are the 2 outputs to turn on the relays. Now we've made 2 different code, one for latching contactors, one for relays, because the relay option has a continuous output from these 2 pins, and it switches every hour. So again, what happens is we momentarily, well, when we start up the motor, it runs for an hour, and then it will turn off power to the Hall and there's the transistors or MOSFETs, and then it will, it will activate. Well, at startup, it will activate one battery. Click. It will start with this one, and then it will go to, after an hour, turn off the motor for a split second, and then it will pulse this one. Click, and then it'll turn back the motor back on, so that it won't have a problem with the rotation. It won't stop the motor because it's about a half a second that it does that. And then the new code that we've also done as an option, where we have this constantly on, and then we flip to this one constantly on. And that way, if you want to activate a relay that requires constant on, you have that, as opposed to the latching relay. So we have the 10 amp option for the latching contactor, which doesn't draw power continuously as a regular relay would. So that's that option. Now, just beside it, pin number 7, you'd have to activate that. So that becomes the regular run Hall right here. And pin number 2 right here, the normal Hall that we've used, is the startup. And then, like I said, we have these 2.2 microfarads. Now these are where I had the 1 microfarad is what we have generally supplied with the kit the last several months or so. And so I just have 1 leg connected there because I did that first at 12 volts, and then I added these for the 24 volt model demonstration. You could see, if you were looking at the oscilloscope, I didn't get a chance to look at it when I started up, but I did before, and you can see that the spike was quite high even with that. So there's a lot of energy coming out here that these parts can't even absorb. And that speaks to the whole idea of how the energy is really flowing. And like I talked about in the last video, introducing the Don Smith system with the heavy side current flow, the energy is just all over the place. And this capacitor is a means of collecting some of that energy and using it. It gets shuffled around now in the circuit. So the input battery is not going to charge down at the rate that you really think it was discharging. Like I said, when I was putting this is the input from this battery here, and I had it across here for convenience, the negative side, but also on the positive side. So this was pulling 4 amps, 3.8, 4 amps. And then when I came down to the T, after the T, so this is what's going straight into the input coils, right? This right here was 6 amps. So that means the power is coming also from this input, or this charging battery. And yet the charging battery is still charging. So that's something that makes you scratch your head. This is the diode. It's got 2 inputs, 1 output. Don't confuse it for a MOSFET. These are the 2 MOSFETs. These are the really good MOSFETs. And very high speed, very low resistant MOSFETs. Resistance MOSFET. So that's it pretty much. Let me look at the Arduino. So this is the Arduino option where it has the chip, and so this chip can be replaced. We can program it. We are not making the code available because it would just, people would presume upon our customer service and want to figure out how do you program, how do you do this, how do you do that, and then they would change it and say it doesn't work when they change the code, and we're not going to deal with that. We're going to provide just the chip, and that keeps some of the things there a little bit proprietary. But again, we'll make the options available for like $2 for the chip. That's all it costs. So what else is there to know? People wanted a close-up, so I gave it to them, and I think that's pretty much covering it. Like I said, let me just describe this so people understand. So the black wire again goes to the bottom of the coils, and it comes to each of the center terminal, which is the same as the backing of the MOSFET, which is the drain, the D, and the MOSFET. And so then that's also over top of this outside leg of this diode, and the other outside leg of this diode they're sharing, and then they're coming out through here. So like I said, this is kind of a bottleneck system here of resistant, but very low resistant diode there. So that's about it. This motor is now a piece of artwork. It is really functioning well now. I'm really excited about it. I mean, it's where it's at. There isn't really much more to do on it that I can think of. So I thank you for watching, and I hope you enjoyed this. I think eventually what we'll do is make, run some different loads on this, as well as the bigger motor. And that way, some people have asked for I was going to run the bigger motor on the big generator coil and all that, like I did a couple years ago with the previous model, and I just kind of ran out of time. I thought the fan was sufficient to show a really big load, give an idea of the kind of output. And that's only at 24 volts. It can go higher than that. So the same with this. Once we get up to 48 volts, this thing's going to really need to be loaded down because it's going to spin really fast. So, but anyway, there you have it. Thanks for watching.